our last section, we dealt with sequences. And in this section, we're going to start looking at series. Now, it might seem like those two things are about the same and that the words are interchangeable, but they're not. Okay. You might remember from last time that we wrote a sequence this way. Okay, that sequence might have, a sub 1, a sub 2, a sub 3, and so on. But if I take all these elements and they add them together, so I use summation as n goes from 1 to infinity, then I get a sub 1 plus a sub 2 plus a sub 3, and so on. Okay, this is a sequence. Just the list of elements. This is a series. To find the sum of this infinite series, let's look at the sequence of partial sums. Okay, the sequence of partial sums is denoted this way. S sub 1 is equal to a sub 1. S sub 2 is equal to a sub 1 plus a sub 2. S sub 3 is equal to a sub 1 plus a sub 2 plus a sub 3. And just continuing in that fashion. If this sequence of partial sums converges, then the series is said to converge. It has the sum indicated in this definition. For the infinite series, of a sub n, the nth partial sum is S sub n equals a sub 1, a sub 2 plus a sub 3, all the way up to a sub n. If this sequence of the partial sums converges to S, then we say that this series converges. If S of n diverges, then the series diverges. Okay. As we're going through this chapter and we're looking at series, there's two questions that we always want to know about series. And the first one is, does the series converge or diverge? And then the second question is, if the series converges, where does it converge? What is the sum? So we'll be looking at those in this chapter. Let's look at some series. Okay, and this would be, 2 to the n, when n is 1 would be just 2, so this would be 1/2, and then the next element would be 2 squared, so 1/4 plus 1/8 plus 1/16. Okay, so our first partial sum, s of 1, is just the 1/2. Our second partial sum, 1/2 plus 1/4, so 3/4. S of 3, we take the 3/4 and add an eighth to it, which would give us 7/8. Okay, all the way down to S of n, which is going to equal 1/2 plus 1/4 plus 1/8 plus everything up to 1/2 to the n power. And I can write this as 2 to the n minus 1 over 2 to the n. That's the n power. Okay, we know this because the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n is 1. As n goes to infinity, these numbers become very large, and the minus 1 really doesn't matter. So that's why we can say it goes to 1. Let's look at another example. I have the sum, n equals 1 to infinity, of 1 over n minus 1 over n plus 1, which would be equal to 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4. Okay, now you might notice in this summation, I've got a negative 1/2 and a positive 1/2, so they're going to cancel each other out. I have a negative 1/3 and a positive 1/3 that will cancel out. And as I go on, all of these numbers are going to cancel out except for the 1. Okay, so we could say that S of n is equal to 1 minus 1 over n plus 1. And again, as n gets very, very large, I'm taking 1 and dividing it by a very large number. So this term goes to 0. And so the limit as n goes to infinity of S of n is just 1. So we would say that this series converges. And just for future reference, this kind of a series where terms have a negative and a positive and they cancel out, we call a telescoping series. It's just like a pirate's spyglass. You know, you can squish it together and have it be much smaller than the original. I can kind of squish this summation together, take out all these terms that cancel out, and make it much smaller and simpler than the way I wrote it originally. Now we're going to work a problem where we write a series in that telescoping form. So we're going to start with and I'm going to rewrite this a little bit. 2 over 2n plus 1 and 2n minus 1. Okay, and if I break this up using partial fractions, I get 1 over 2n plus 1. Excuse me, that's minus 1. Minus 1 over 2n plus 1. Okay, now let's look at a couple of these. Okay, if I start with n equals 1, this is going to be 1 over 2 minus 1, so just 1 over 1. And then this one will be 1 over 2 times 1 plus 1, so 1/3. So minus 1/3. Now I'm going to let n equal 2. In which case I'm going to have 1 over 4 minus 1, so 1/3. And here I'm going to have 1 over 5, so minus 1 over 5. When I let n equal 3, I'm going to have 1 over 6 minus 1, so 1 over 5, minus 6 plus 1, so 1 over 7. And I think you can see that I'm going to have these positive and negative pairs of numbers that are all going to drop out. So I'm going to end up with, at the end, I'll have the 1 that I started with plus minus 1 over 2n plus 1. Just this last little term here won't have something to cancel out. Okay, but as n goes to infinity, this part goes to 0. So my sum is actually 1. Let's write it this way. The limit as n goes to infinity of 1 minus 1 over 2n minus 1 is 1. Okay. Let's look at another kind of series that we work with quite often. And this is called a geometric series. If I have a sum where n goes from 0 to infinity of a times r to the n, I can break this down as a plus ar plus ar squared plus ar cubed and so on. And if we say that a may not equal 0, we call this a geometric series. Okay, the r is called the ratio, and the ratio also may not be 0. Okay, now for a geometric series, if the absolute value of r is greater than or equal to 1, the series diverges. Okay, because I'm multiplying by more and more r's. If these are bigger than 1, this is going to get bigger and bigger and bigger. But if the absolute value of r is less than 1, then that series converges. Okay, as I multiply by more and more r's, when I multiply by something that's less than 1, my result is smaller and smaller. And when it converges, we can say that this sum, n equals 0 to infinity of a times r to the n, is equal to a over 1 minus r. And again, this only applies if the absolute value of r is less than 1. Okay, so this is a quick, easy way to find the sum of a geometric series. In this example, we'll look at one each of a converging and a diverging geometric series. So let's start with this one. Okay, I could rewrite that as 3 times 1 over 2 to the n. And I could even put the n out here. So now this is my a, and this is my r. And I could take the a outside and just say 3 times the summation of one half to the n power. Okay, using my formula, s is equal to a over 1 minus r, I'm going to have 3 over 1 minus 1 half, which is 1 half. And so this is 6. Okay, so this was a series that had a ratio that was less than 1. Let's look at another series. Okay, this one looks very similar to the other one we had that was 3 over 2 to the n. But this time, the 3 is part of the ratio. It's the thing that we're multiplying by. Okay, I don't have anything out here, so I could say that a is 1 and r is 3 over 2. And because this absolute value of r is greater than or equal to 1, we know that this diverges. And again, when I multiply by a number bigger than 1 repeatedly, my answer is just going to get larger and larger and larger, so it diverges. Let's look at how we can construct a geometric series for a repeating decimal. I want to write 0.08 as a ratio of 2 integers. Okay, to do that, let's think about this first 0.8. If I wanted to write this as a fraction, it could be 0.8 over 100. This is 8/100. And then the next 0.8, the first repeat, would be 0.8 over 10,000. Okay, we have to add 2 zeros because this is a 2-digit repeat. And then we would have 0.8 over 10 to the 6th and 0.8 over 10 to the 8th, and so on. So in this case, we're going to say our A is 0.8 over 100, and our ratio, what are we multiplying here? 1 over 100. Okay, we just keep adding 2 zeros and 2 zeros and 2 zeros. So we could say that the summation as n goes from 0 to infinity is 8 over 10 squared times 1 over 10 squared to the n power. Okay, so using this a and this r, I can write 8 over 10 squared over 1 minus the ratio, 1 over 10 squared. So this is going to be 8 over 99. And if you put this in your calculator, 8 over 99, you should get 0.80808080, etc. So that's a way to change a decimal, a repeating decimal, into a fraction. Before we move on, I want to look at some properties of infinite series that will help you when you need to evaluate them. So I'm going to call this sum of a sub n. We're just going to call that a, and we'll call this v. Okay, and we're going to say c is a constant. So if I have the sum of c times a sub n, that's just c times a. And again, I can take that out here if I want to. If I'm going to add two summations, I just can do each one separately. I just have a plus b. And the same thing applies if I have a sub n minus b sub n. That's just going to be a minus b. Okay, so those are some properties of infinite series. Okay, another important concept that we're going to look at is called the nth term test for divergence. And it goes like this. If summation of a sub n converges then the limit as n goes to infinity of a sub n equals 0. And we can say if the limit as n goes to infinity of a sub n does not equal 0, then the summation of a sub n diverges. Now let's use the nth term test for divergence. I've got a summation here, n equals 0 to infinity of 2 to the n power. And if I take the limit as n goes to infinity of 2 to the n, well, that's going to be infinity. So the limit of the nth term is not 0, and so this series diverges. Okay, let's look at another one. This one I have n factorial over 2 n factorial plus 1. So again, we're going to take the limit of n factorial over 2n factorial plus 1. What's going to happen here? We know that factorial gets large very fast. And so pretty soon this 1 is just not going to matter at all. And I'll have n factorial over 2n factorial. The factorials will cancel out, and I'll be left with 1 over 2. Okay, but the limit is not 0, so this series also diverges. Okay, let's look at one more. And we know that the limit as n goes to infinity of 1 over n, this does equal 0. This time, because the limit is 0, the nth term test doesn't apply, so we don't know if this converges or diverges. Okay, we're going to wrap up this section with a bouncing ball problem. In this problem, we have a bouncy ball. We drop it from 6 feet up, and it travels down to the floor, and then it bounces up, but it doesn't ever quite bounce as high as the last time it goes up. So it bounces up and comes down, bounces up, comes down, every time a little bit lower than it was before. And what we want to know is how far up and down does that ball go as it's bouncing. Okay, so we're told that the first distance is 6 feet, and for each bounce the ratio between the previous bounce and the new bounce is 3/4. It only goes 3/4 as high as it did. So to find the total vertical distance, we could say that D1 is 6 feet. That's this first fall. And then D2 would be 6 times 3/4. That's when it comes back up, and then it's going to fall down 6 times 3/4. So we get 12 times 3/4. And then if we wanted to do the same thing for D3, we're going to have 6 times 3/4 times 3/4 plus 6 times 3/4 times 3/4, which is going to give me 12 times 3/4 squared. Okay, so we can keep repeating this process, and we're going to continue to have a 12 out here, and then 3/4 to higher and higher powers. So my total distance D is going to be 6 plus 12 times 3/4 plus 12 times 3/4 squared plus 12 times 3/4 to the third power, and so on. So I'm going to write that as 6 plus 12 times the summation as n goes from 0 to infinity of 3/4 to the n plus 1 power. Okay, we started at 0, so we have to use n plus 1 to get that first 3/4 in there. And this now gives me 6 plus 12 times 3/4. I'm going to take that term out. So that I can do this. Instead of having that n plus 1, now I can have just the n. So I'm going to have 6 plus 12 times 3/4 is 9 times my a. I don't have anything in here, so a is just 1 over 1 minus 3/4. 1 minus 3/4 is 1/4, and the reciprocal of 1/4 would be 4, so it's going to be 6 plus 9 times 4. So this is 36 and another 6, 42 feet. Okay, so our ball is going to travel 42 feet before it stops.